Good evening, everybody. I'm just doing one sound check just before we fully get started. I'll get a thumbs up from the people outside when they can hear me. Yeah, good. Okay, so it's my great pleasure to introduce you to Professor Artemis Spyrou. Artemis achieved her PhD in 2007 at the National Technical University of Athens in Greece, and she's been with us here at MSU ever since. For 4 years upon joining at MSU, Professor Spyrou was the Associate Director of the Education and Outreach at the Facility for Rare Isotope Beams, also known as AFRIP, as you'll be hearing more about today. And then following that, she was the outreach academic advisor for the facility. So Artemis's research is focused on nuclear experiments, which are important for understanding astrophysical phenomena, and I'm sure we'll be hearing a lot about that more today. I'd also just like to thank the MSU Library for allowing us to use this digital space, and for Elias for doing the social media for this event. So let me hand you over to Artemis. Thank you very much for joining us. Here's your clicker, and here is the mic, and I will get out of the room.
Thank you very much, Dan. Let me mute this for a second so I can install. Okay, we're back on. And since I'm alone in the room, I will take the mask off. Okay, hi everyone. First of all, I'll thank Dan, Hayden, and the rest of the group for inviting me to give this lecture. I am always excited to share my research on the topic of nuclear astrophysics. So this is what we'll be talking about today, the synthesis of elements in the stars and in the lab. So there are 118 known elements. We start with hydrogen up here, which only has its atomic number 1, which means it has 1 proton in its atomic nucleus. And we go all the way down here, where we have the heaviest known element, which is oganesson, OG, with 118 protons in its nucleus. So there are, out of these 118 elements, 90 we can find naturally on Earth, and 28 are artificial. If you look around, you cannot find any of those elements, and we had to make them in the lab in order to study them and even discover that they exist. And so in this picture, the artificial ones are the ones that are marked with the white color. So up to now, we know up to oganesson, the element 118, but this is not the end. There's still ongoing experiments trying to discover more and more elements, and we don't really know where the limit is. We're still searching. There's theory, predictions, but we don't really know where the limit is. So we're still searching. So everything we see around us is made out of these elements. This is what we have available, and this is what our world is made of, and everything is made of. And I chose one item that we all have in our hands almost every day, a smartphone, which is quite exotic because it has many, many different elements, probably one of the most complicated devices. It has 54 different elements that can be found in a smartphone. On average, I imagine different smartphones will have different. But this includes elements that we all know very well, like hydrogen, and we have here iron, nickel, silicon. There's a lot of known elements out there, and there's also some not quite as known ones, maybe more exotic ones, like if you see down here, ND is for neodymium, and PR is for praseodymium, and so on. So there's those smartphones that you hold in your hands every day. They're quite exotic items. But it's not just the items or the objects we see around us that are made of these elements. We are made of the same elements. So So if you look at the elements in a human body, there's 41 elements. Actually, if you look at different sources, you will find that number varies a little bit, but this is one of those numbers. Most of the elements, we know exactly why they're there and how much of it we have and why we need it. And these are the ones that are marked in green in this picture. And then the ones in orange and the ones in this yellowish color, we know there are traces of those elements in our bodies, but we don't really know exactly what they're doing. And some maybe we do and some not so well, but it's, there are elements in our bodies that we are not so familiar with yet. But it's not just what elements are there in a smartphone or in our bodies or in the universe in general. It's also how much of it is there. So that's another observable, that's another piece of information that we need to worry about. So if I continue with the example of the human body, we know that we are mostly made of water. So there's 62% water, and there's this protein, fat, and so on. So there's the different elements make up what we consist of. And if you look at the various elements, we have oxygen and carbon are the dominant ones, and of course hydrogen. So the hydrogen and the oxygen that make up water in our bodies. And then everything else are in smaller quantities, down to trace elements, very, very small quantities, but still some of them are really, even at small quantities, they're very useful for the body. So why am I telling you all of this? This is just part of us, right? We sit around and we care what goes into our bodies. Maybe we try to be healthy and take care of our bodies. We also care about our history. And we say, okay, where are you from? Where was your family from? Your grandparents, your grand-grandparents. And you kind of track in generations of where you came from. This is part of this origin. Where did every single atom and every single nucleus in that atom in our body, where did they come from? And this is what we are talking about today. So to answer that question, the first few elements on this periodic table of the elements, that's hydrogen, helium on the other side, and lithium, just the first few. These elements were made during the Big Bang, long time ago. So right after the Big Bang, if we were looking at the periodic table of the elements, this is all we would see. Quite easy, simple periodic table. Everything else we see around us was made inside stars. Now you could easily ask the question, how do we even know that? Maybe everything was made during the Big Bang. Why do we think that they are made inside stars? And the answer, or the original answer, came from one of those artificial elements that I talked about, those white circles, those white fonts, the technetium. Technetium is from the Greek word technito, which means artificial. So this was the first artificial element discovered. And this is the main reason why we know, or how everything started, how we discovered that all of these elements are made inside stars. The story goes something like it was a long time ago at Mount Wilson Observatory. We see the picture here. It was an astronomer called Paul Merrill, and he was making observations of various stars. This is one of the spectral lines that he was observing of those stars. And at the time, people knew where the energy in the stars is coming from, probably through nuclear reactions, which we'll talk about more later, but maybe it was mainly the lightest elements, and they didn't really have a direct observable to say that, okay, this star is making new elements or not. Maybe they were all coming from the Big Bang, as I mentioned already. So to his surprise, Paul Merrill saw these lines here that corresponded to technetium. Now, why was this a surprise? The longest lived technetium nucleus that people knew at the time would live for about 4 million years. You see it down there. So for a Big Bang that happened a few billion years ago, if technetium was made during the Big Bang, and it only lives for 4 million years, that means that all of the technetium created during the Big Bang should have decayed away. But if you see a star with technetium there, that's a huge surprise. It means either, through the words of Paul Merrill at the time when he presented his discovery, he said, well, either the technetium, there is actually a stable technetium that we haven't discovered yet, or this star is making the technetium, or some other star is making technetium and somehow this made it into this star that I'm looking at. Well, there is no stable technetium. To this day, we haven't discovered any stable technetium. And so he was right that the star was making the technetium, and that was the first discovery, and that kind of triggered the whole field of nuclear astrophysics and nucleosynthesis, so the synthesis of elements in stars. Okay, so I wanted to go back to this because we're talking about where are all these elements coming from. I'm sure you're waking up in the middle of the night thinking, where is the molybdenum in my body? Where is this coming from? I'm sure that keeps you awake at night. Well, I'll tell you where that's coming from, but I'll also tell you that this is not the right question to ask. So when you ask where are the elements coming from, this is the word elements there, that's a little bit too broad. We need to focus it a little bit more because one particular element could be coming from many different environments, and so it's important to ask the right question. So to get to the right question, let me just go through a little bit of introduction to nuclear physics, just for everyone to be on the same page when we're asking the right questions. So let's just look at the human body again. It's our example. You could do this with anything. This is Katerina. This is my youngest daughter. And she's about 1 meter tall. We'll use her as a scale. Well, Katerina is made about 60% of water. And so the water molecules would look something like this. There's oxygen, and there's 2 hydrogens attached to that oxygen. Now, if I zoom into one of those oxygen atoms over here within the molecule, then we'll see that the atom of oxygen has a central nucleus, and then there's the electrons, the atomic electrons flying around. And the thing that we're more interested in is the nucleus itself. So let's see, the nucleus consists of protons and neutrons. Let's say our protons are green and our neutrons are yellow in this example. And oxygen itself, it has 8 protons. That's what makes it oxygen. And it could have different numbers of neutrons. But the thing that makes it oxygen and defines its chemical properties is the fact that it has 8 protons. And so everything we're talking about here, it has 8 protons. This means 8 electrons, and those 8 electrons will connect within the molecule. That's why it's important on the chemistry side. It's very important the fact that it's 8 protons. The neutrons, they don't do so much in terms of the atom and the molecules and so on, and so it can be a different number. Protons have charge, electric charge, and neutrons don't, and that's why it kind of makes it easier to add and remove those neutrons. In terms of scales, I mentioned Katerina is about 1 meter tall. The molecules are about 1 billion times smaller than the 1 meter. That's 10 to the minus 9 meters. Just for scale, one of Katerina's hair, if you would look at it, that would be 10 to the minus 4. So that's almost 1 billion times smaller. So that's the molecules are pretty small. If we go to the atom, each of the atoms is another factor of 10 smaller than the molecule, so that's 10 to the minus 10. And if you look at the nucleus itself, then you get to 10 to the minus 15. So that's a huge difference, right? It's 5 orders of magnitude. It's a 1 with 5 zeros next to it. That's how much smaller the nucleus is compared to the atom. Just to get a sense of a scale, if we go to the Spartan Stadium and our atom is the Spartan Stadium, the nucleus would be a little golf ball right at the center of the Spartan Stadium. This is how much bigger the atom is compared to the nucleus, and this is how much empty space there is in our bodies, in the floor, everything we see around us. There's a lot of empty space. That's why when we talk about nuclear reactions happening, even in the lab here, but also in the stars, These are hard reactions to happen just because there is so much empty space, and nuclei have to get close together to interact. Okay, so get into how do you ask the right question in terms of where we all come from and where all these atoms and those nuclei are coming from. I mentioned before that the number of protons is what defines what element it is, but the number of neutrons could vary. And so in our oxygen example, if it's 8 protons and 8 neutrons, the sum of this is 16, and so this would be called oxygen 16. This is the most common form of oxygen. When we're breathing, we are breathing mostly oxygen 16. So when we say our body is made of majority oxygen, then there is a lot of oxygen 16 there, but it's not just oxygen 16. I could add a neutron and have 9 neutrons, and still 8 protons. That would be called oxygen 17. This is another stable form of oxygen. So the air we breathe has oxygen 17 as well, and it also has oxygen 18, 10 neutrons. We can keep going. We can add 1 more neutron and have 11 neutrons and 8 protons. That's oxygen 19. You see I changed the color here because this is not stable. The air we breathe does not have oxygen 19 at all. If we want to study it, we have to make it in the lab. And the same on the other side. We can remove neutrons, and oxygen 15 and oxygen 14 have fewer neutrons, and we can keep going in both directions. There are limits that I'm not going to talk about today, but there are a lot of these what we call exotic isotopes, or radioactive isotopes. And while all of these have the same chemical properties, their nuclear properties are very different. And this is very important. This is also important for when we use these kind of different isotopes for medical applications, for example, or any kind of application. You can choose the properties that you want based on the chemical properties. They're all oxygen, but then also the nuclear properties. How much energy is released when one of these nuclei decays into something else? What kind of particles are emitted? How long does it live? All of these are important properties that are part of the properties of this isotope. So the stable isotopes that exist naturally on Earth, when we talk about oxygen, are these 3, and then everything else are either made in stars, or we can make them at the lab and study them, or both. Just to get a sense of the time here, these 2 guys live for a couple minutes each, and oxygen 19 is 26 seconds. And if you keep adding neutrons or keep removing neutrons, then those, we call these half-lives, it's just how long they live, they become shorter and shorter. Okay, so based on all of this, now we can ask the right question. The question is not how are the various elements formed, but really how is each of these isotopes formed, because each of them might be formed in a different way. So if I go back to my chart of nuclei, the periodic table of the elements for the human body, and the question that's keeping you up at night, how much molybdenum do we have in our bodies? It's not a lot, by the way. Well, you should know that, or where is all that molybdenum coming from? That's actually the question. Well, I can tell you that molybdenum has several different stable isotopes. So when we talk about molybdenum, it includes 1, 2, 3, 4, 5, 6, 7 stable isotopes, and they're all there all the time at different amounts. And where they're coming from, well, these 2 first guys have fewer neutrons. They're made in some kind of a supernova in a process called the P process. We're not going to go through the details of these processes, but just putting it up there, I'm happy to answer questions at the end. These middle guys here are made in a different process. It's called the S process. S is for slow. In a different kind of star, in AGB stars, asymptotic giant branch stars. And then these more neutron-rich ones, they're made in a process called the ARP process that we are going to talk a little bit more about the ARP process. And it's a process that we have evidence that's happening in neutron-star mergers. That's quite exotic events. Maybe some contributions from supernova, maybe some contributions from other processes. Who knows? So there's a lot going on about molybdenum and every other element, really. things are complicated. The universe is complicated and stars are complicated, and you can have contributions from many different processes. And so that's why the question, where is molybdenum coming from, becomes so much more complicated when we're looking at every single isotope and where each one is coming from. So now that we've seen our molybdenum example, I also wanted to introduce the chart of nuclei, which is what's hiding behind all of these pictures. Let's see if we can go back. There we go. So each of those elements that we saw in our periodic table of the elements, each one of the boxes corresponds to one element. Well, when we talk about nuclear physics and we care about the individual properties of these nuclei, then we grab that one box and we develop it into a row. And so the row for molybdenum would be this guy right here. So it has all of the isotopes of molybdenum. The row for oxygen is sitting down here. Oxygen has 8 protons, and so it would be Z equals 8. That's our proton, and so on. So every element has a different row over here. And so the way that on the periodic table of the elements, we put different colors depending on what we want to highlight and so on. In the chart of nuclei, we do the same. We use different colors to indicate the different half-lives. This is what these colors are for, or the different types of decay. So this is what we use every day in our research. And another thing we do is put all of these various astrophysical processes. We also put them on the chart of nuclei just to see what is involved in these processes. And so, again, I'm not going to go into the details, but the normal evolution of a star will go through this area over here, which is called stellar burning. And then for heavier processes, we go, for heavier elements, we go through various different processes. And for this talk, I wanted to focus on one particular process, which is this R process. It is quite an exotic process. It's something that we research a lot here at MSU, at the Facility for Rare Isotope Beams, and at many other places around the world. There were the gravitational wave discoveries recently. There's electromagnetic observations. There's a lot of excitement about the R process, and so I wanted to mention that. Just to get a sense of the connection between nuclear physics and astrophysics, I wanted to just show just a picture here. It's again, green are the protons and yellow are the neutrons. And so this would indicate the lightest nuclear physics process or reaction sequence in the stars. That would be all the way down here. It's a process that's called the PP chain, or hydrogen-hydrogen chain. And just to get an idea, let's say we are in an environment that only has hydrogen. Well, the 2 hydrogen nuclei could fuse together to make something else. And then whatever you make could grab another hydrogen from the environment and make something else. And so this is just step by step how we go and we build heavier and heavier elements. The PP chain uses 4 hydrogens to make 1 helium-4 nucleus. There's our helium-4. And when we're at these lighter masses, things are simpler, and we can use our cartoons like these or little arrows on the chart of nuclei, and it's easy to see which reactions are dominating, what is going on. But when you get to a process like the R process, you get to nuclei that there's a huge number of nuclei that participate in that process, then you can't anymore just track one by one and see what's going on. You have to do this through simulations. This is one example of such a simulation. This corresponds to an R process. There's a lot of information that you can ignore on the slide. This is from a research presentation that is trying to highlight what is going on, what is the flow within the R process. This immediately shows you which nuclei are participating in the R process, and so these are the nuclei that are important, that we need to study their properties and we need to study their reactions. And so this is how we know which nuclei to focus on. And it also gives you this one, if it evolves all the way at the end, it will show you the abundances of all these elements. And this is our observable. This is what we have to compare to what we see in the universe. And so this is how we know that our model works and we have an accurate description of the universe or of the particular stellar environment, or if we're missing something. So on the nuclear physics side, where I come from, what we're trying to do is study the properties of all of these nuclei. My video is not working so well. This is supposed to just keep going and going and going and going up to the heaviest elements. And this is an explosive process. So all of this takes about a second to complete. And then whatever you made, these are all very exotic, short-lived nuclei. And whatever you made will just slowly decay back to these boxes here, which are the stable isotopes. So this is, again, our final observable. This is what we have to compare to what astronomers observe. But yeah, this gives you an idea already. What are the nuclei that are participating in this process? And so it's an excellent guidance for us to see where to focus our experiments. So it's not just which nuclei, but you also need to know what are these nuclei doing in this process. And so let's just zoom in here, just zooming into this region, and let's just zoom in some more, right around the R process path. So for an R process, what's happening is that the environment has a lot of neutrons. And so if somehow you made it into this red box here, what's going to happen is that your nucleus could capture a neutron and go this way, just one more neutron, so it goes to the right. Or, so this N gamma here just means it's capturing a neutron and it's just emitting radiation. Or it could decay. This is a process called beta decay. So it could decay and go this way. So immediately you see that the beta decay all of a sudden made a new element. It helped us go heavier. And the neutron capture just stays within the same element, but it makes it more exotic. So then this guy could decay later. So the competition between those two is the most important thing that we need to focus on. Of course, things are always more complicated, so there might be other things happening at the same time, but this is the main thing. It's a competition between a reaction, a nuclear reaction, which is the neutron capture, and with the beta decay. These are the things that we need to measure. On top of everything, if you do go all the way to the heaviest masses, then those nuclei undergo what we call fission. This is a known process that is used like for energy production in reactors. This is the main process that is happening there. And what happens is that heavy nucleus just breaks into two pieces, and this is what this graphic here indicates. So there's a lot going on, and there's a lot that we need to worry about. So we need to know, now that we know what is going on, what are the properties we need to measure, we also know which nuclei we need to study. Let's see the status. What have we done so far? So this is, again, another version of the chart of nuclei. I told you from the beginning that the chart of nuclei is our favorite thing. It's our playground, and we plot everything on this chart. The R process that I keep talking about is this blue arrow here, and the black boxes correspond to the stable isotopes, just for orientation. The darker color that you see here are the nuclei that we know something about, not necessarily everything, but we know something about them through experiments. And this is done. I have two examples here of two facilities, kind of state-of-the-art facilities that are operating today. Actually, this is alive. This one just shut down to start the new facility that I will be talking about very soon. And Riken in Japan is the competing facility. But these facilities and other facilities around the world have been producing and studying isotopes over here. Now you'll see that there's a little bit of a distance between where this blue arrow here is for the R process and what we know already. And this is the problem. So we are doing all these experiments. We are learning so much about nuclei, how they work. We are improving our models. We're improving our techniques. But we're still not where we want to be in terms of studying the production of the heavy elements through this exotic process, through this R process. And this is why we need to build we're almost there, we needed to build a new facility that will get us exactly where we need to be. And so this orange line over here in the back, this line, is the reach that we're going to get with the new facility, the facility for rare isotope beams. And you can see that the most part, all the way down here and here and here, almost for the lightest of the nuclei, it will give us access to the important nuclei. And that's why the whole community in the US and really in the whole world, we're all excited to have access to the important nuclei and be able to study them and understand this element production in the universe. Okay, so where is this facility? We are in Michigan, right here, the center of Michigan. That's where Michigan State University is. And there are two facilities in one, as I mentioned. One is the National Superconducting Cyclotron Lab that just stopped its operation. And the other one is the Facility for Rare Isotope Beams, or AFRIP, which we are almost ready to get started. They're both under the same roof, working with the same people working there. You see a picture. If you're anywhere close by, this is Shaw Lane. This was from one of our open houses. People, before COVID, people waiting in line to get in and see the facility and the equipment and talk to our scientists. It is the largest nuclear physics group in the country, and it is the #1 nuclear physics graduate program in the country. So we are very proud of our facility and our department. It is connected with the Department of Physics and Astronomy and with the Department of Chemistry and with engineering within campus. And so this is a unique facility to have such a large national user facility on the campus of a major university. So education and outreach go hand in hand at this facility. Okay, so what is AFRIP? AFRIP, or the Facility for Rare Isotope Beams, is a project that started about 10 years ago with support from the Department of Energy, Office of Science, from Michigan State University, and from the state of Michigan. It's a $730 million project. As I said, it started about 10 years ago, and it's almost ready for completion. The official completion date is June 2022, but we're working towards early completion, so we're all hoping that by the end of this year, maybe early next year, it will be ready and we can do our first experiment. It is a facility that, it's a brand new facility, but it's sitting at the same location with the same team that has been running this kind of experiments for over 50 years. So MSU celebrated 50 years of BEAM a few years ago. So there's a lot of experience and, of course, bringing in new expertise from the outside and people from all over the world really coming to AFRIP for experiments. So there's, as I said, a lot of excitement, not just from the local group, but from the whole country and from all over the world. Just to get an idea of what AFRIP looks like, here's a nice video. You can also find this online on our YouTube channel or on our website. But AFRIP sits underground in a tunnel. It is a linear accelerator that kind of loops twice in the form of like a paperclip. And so you have to start with something that you can find on Earth. This is your starting point. You cannot start with something exotic already. And so you start with atoms that are found on Earth, and then you strip out their electrons so that you can accelerate them more efficiently. Once you do that, you get those nuclei, you get them through the linear accelerator and they speed up. They go really fast. They go about 50% the speed of light. This means going around the Earth 4 times in a second. That's how fast they go. And then they hit a target. This is a piece of metal. It can be, our target can be anything. And once these nuclei hit the target, they will break into different pieces. It's not the same thing that happens every time. Every time it's something else that is happening. So out of all the different pieces that are coming out, there's typically this one nucleus that we're interested in. We're not interested in everything. So you have to have a nice filter that kicks out left and right the ones that you're not interested in. If they're heavier or if they're lighter, can kick them out, and you just keep the beam, as a beam, you keep the ones that you are interested in. And then you deliver them at your experimental station, whatever that station might be. It could be to measure a nuclear reaction. It could be to measure the mass of these nuclei, their decay properties. There's a lot of things that we can do with these nuclei. So just to do this a little more slow motion, this side here is the AFRIP Accelerator. This is where the magic happens in terms of getting our beams at these high energies or high velocities. And then somewhere here is where the target is, and that's where the reaction happens. And you start with something that is stable and known, boring you could say, and smash that and get something exotic that maybe no one has ever seen before. You discover a new nucleus. And then once you have that secondary beam, once you have that new nucleus, then you're going to guide that into the experimental stations, and this is what everything in blue here looks like. It's the various experimental stations, and again, you can do many different experiments with them. I brought with me a little demo that I want to show you that just demonstrates a little bit this kind of fragmentation process. How do we make our nuclei? So let me roll this in. There we go. So this is what we call the Home Depot Accelerator. There we go. So what this accelerator has, so this part right here is our accelerator. It's the thing that will make our nuclei go fast. I have my nucleus, the initial nucleus. This would be the initial beam, a stable beam. If we count the number of protons and the number of neutrons, you will see that this is carbon-12. It has 6 protons and 6 neutrons. And so this is stable. We can find this everywhere. And in the box right here, you can see I have another carbon nucleus. And so the idea is that you would have to get one of your 2 nuclei going very fast. They hit the other nucleus, and then hopefully what comes out will be something new and exotic that no one has seen before. And then we study their properties. Let's just give it a try. There we go. So here it looks like we're only left with 4 protons. So 4 protons would be beryllium. And then we have 1, 2, 3, 4, 5. We still have 6 neutrons, so that gives us beryllium-10. Beryllium-10 is an unstable nucleus. It's not stable, so we did make something exotic. It's definitely different than the carbon-12 that we started with, and so this is kind of how we do our experiment. Then if I try another one, we'll try again. Here's our carbon-12. Go in. So this time we have, again, it's 4 protons. So again, we made beryllium. But this time it's only 5 neutrons, so we made beryllium-9. So we did make something different. So every time you do this, you will make something different. And it's just a probability distribution of how many of each you are going to make. Now imagine that you can do this, exactly what I'm doing. Imagine you can do this about 1 billion times every second. This is how much beam we have, probably even more than that. And then 1 billion of these nuclei every second will interact with the target nuclei, and then you get something new out. And this is how the experiment works, and then we just need to select the isotopes that we're interested in. Let's just go back. Get this guy out of the way. Okay, so I also wanted to show you what things actually look like in real data and not just with the demo. So with the demo, we ran it twice, we made 2 different nuclei, and that's it. So when you actually run your experiment, things are obviously a lot busier and more complicated, but it's pretty cool to see. So let's say this is what we call the separator in AFRIP. This is our filter. Whatever comes in, you have electric and magnetic fields that will select based on the mass of the nucleus and the charge, it will select the ones that you want. So let's say we start here with our primary beam of calcium-48. Calcium-48 is a stable isotope. You can find it in nature. It's rare, but it's stable, and you can find it. And let's say the goal of our experiment to make magnesium-40. That's a pretty exotic magnesium. So magnesium 24 is the stable, kind of the most common form of magnesium. And now we're at magnesium 40. That's a lot more neutrons than the stable one. So if we have our beam hit the target in here and we see what comes out, then everything, all of this comes out. This is where calcium 48 is, this is where magnesium 40 is, and there's a lot of things that are coming out during that experiment. As an experimentalist, I can tell you that I cannot run an experiment looking for magnesium 40 this way because my detectors will be overwhelmed by everything else that's coming out, and I cannot really select and identify my magnesium 40. So that's why we have this filter. If you go through the first stage here of the filter, of the separator, then already you are kicking out most of the unwanted isotopes. See all of those very intense pink isotopes, they're all gone. And you're only left with this distribution here. It's still a lot, and it's still, magnesium is not the dominant one, but we could possibly do an experiment with this, but there's still a lot. I mean, these colors down here are a lot more intense than my magnesium. But if you go through the rest of the separator and you go all the way to the end, then what you're left with is this distribution here. Just a few, what is this? Just 5 isotopes, and magnesium is one of those. And even though it's so exotic, this is something I can do an experiment with. Our equipment is very sensitive as long as it's not overwhelmed by that. But they are very sensitive. We can identify each of these particles within nanoseconds. That's a billionth of a second. That's the accuracy that we have. We can identify every single one of them. So that's something that we can do an experiment with. So once you have your nice beam, your exotic beam, then you send it into whatever experiment you want to do. This is just an example, a collection of detectors. If you like to see equipment, I strongly encourage you to come to the lab for a tour once COVID is over and you can see all of these detectors in person. But depending on what we want to study, if it's decay, if we want to measure neutrons, we want to measure gamma rays, charged particles, depending on what we want to do, we have a dedicated piece of equipment that will do all of this. My own detector that my group mainly uses is this guy here. It's called the sun detector. So I hope I showed you a little bit. I gave you a little flavor of how all these different elements we see around us and their isotopes are made in the stars, and also how they could be made in the lab, and how specifically we do this process at the facility for isotope beams, and why there's so much excitement that the facility is coming online very soon, and what is the important science that we're trying to measure. So there is exciting research happening today. We have the techniques developed. We have the equipment developed. Everything is ready. We're going to get new beams that we have not had access to before, brand new isotopes that no one has ever seen before, and this is what the facility is going to provide for us. And so we are talking about a new era of rare isotope science, and there's a lot of excitement, as I said, not just from the local group, but from the whole country and from the whole world who's coming here for experiments. And so this is all I have. I just have some contact information if you want to come to the lab for a tour or learn more about the lab. There's the website and my own information if you want to contact me. And for students in the audience, there are a lot of opportunities to get involved with summer schools, and there's the MSU Science Festival coming up. So this is our outreach coordinator, Zach Constant. You should contact him if you're interested. That's all. Thank you.
Okay, so we've got some questions from Facebook and Twitter to ask you. So, and please repeat the question
sure.
After I ask it. So, first of all, Amanda on Facebook asks, is it possible that there's a limit to the number of elements because there are too many particles trying to become bound for that element to exist? So Amanda on Facebook asks, is it possible that there is a limit in the number of elements that exist? The answer is yes. There must be a limit. We just don't know what it is right now. So we know up to the element 118 that we reached experimentally, we know that exists, and we know what theory predicts. Different theoretical models have different predictions, and so it's not
it varies. It has to be constrained by experiment, and then we won't know until we try and we get there and to see if we see a new element or not.
Okay, James on Twitter asks, what is your favorite element?
Okay, the question from James from Twitter is, what is my favorite element? I was going to say molybdenum. I keep making the joke about it. It was molybdenum at some point because that's the main isotope. Molybdenum-92 is one of the isotopes I studied during my PhD. Then beryllium-16 was something excited I did early on when I first joined MSU, so beryllium was my favorite at the time. So it varies. It depends on what's the new experiment that's coming up that we're excited about and what we're learning from it.
I think you just answered this in your last slide, but someone asked, do you do visits during normal times of the AFRIP? So I assume that they could just follow these.
So the question is, do we do visits at normal times? So we do. There's about 4,000 people a year that come for tours of the lab in person. So definitely you should try to come when COVID is over. But we also have about once a month we have virtual tours of the lab live. And if you take a look at our social media, putting up there, then you'll see the dates and you can join one of those.
Okay, Ioana asks, if I said that correctly, Ioana asks, why do you use carbon in the collisions when you do your experiments?
Yeah. So the question, Ioana, there was a question, why do we use carbon? So in general, the cyclotron lab and AFRIP, they can accelerate anything that is stable in principle, from hydrogen to uranium. So for the demo, carbon is just an easy nucleus. We can just count 1, 2, 3, all of the isotopes, the neutrons and the protons. But we can use carbon. We can, as I said, we can use anything stable all the way to uranium.
Okay, and the last one I have for now, but I'll check out there again, is Alex asks, how do you produce the energy that you use to accelerate the particles in AFRIP?
So the question is, how do we produce the energy to accelerate the particles? So this is kind of normal power that powers magnetic and electric fields. This is the main thing that is happening to accelerate particles, is that they will go through, let's say, an electric field, and they get a kick, they get a little push in their velocity, and if you just keep doing that over and over again, then you're accelerating them more and more. In the past, with the cyclotron facility, this was done in a round accelerator, and so every time the particle would go through a particular region of that round device, they will get a little kick from an electric field, and then they go a little bit faster, and then they go again through that and again, and they just go around that circular accelerator. AFRIP is different. It's a linear accelerator, which has the advantage that you can increase the energy or the velocity that you can reach by just adding more and more modules. With the cyclotron, it's limited. It's providing whatever energy it can provide. With a linear accelerator, you can just improve more and more. And so what AFRIP can provide right now and within the year that we can do our experiments, it's we do plan and hope to be able to do an upgrade, which will give us even more energy in the future.
Okay. So I'll keep my mask on, but I'll just thank you if I can take
Maybe I'll put my mask on.
And then I'll grab.
There you go.
Thank you. Okay, I just wanted to say again, yes, thank you very much, Professor Spyrou, for coming and talking to us. I certainly learned a lot about the AFRIP, and it seems there's lots of interest around. So thank you very much for coming, and thank you to everyone for looking in and listening to the talk. So thank you very much, and we'll see you again soon. Okay?
Thank you. Thank you very much.